Hi guys, I'm Dillon, and I'm going to be talking about Aurora Borealis today, aka the Northern Lights. All right, so I'm going to start here. Okay, so it really all comes down to the magnetic field for the Northern Lights, where it starts and where it ends. So here's a magnet I drew up here in this top corner. So the purple is the magnet itself. It has a south pole and a north pole. Now, these black lines are the magnetic field lines. This is just a representation of the direction that they take. And they're just endlessly going in this circle between the north and south poles. Now, this will come in handy later when a charged particle comes in contact with a magnetic field. It'll want to go perpendicular to it. So you can see that gray line here goes perpendicular to the direction that the magnetic field is going. So where it starts for the Northern Lights is on the sun. The sun, like the Earth, has a magnetic pole or a magnetic field. And it's a lot more volatile than the Earth is. So it's constantly creating like solar storms or what we know as sunspots. So you can see some sunspots I drew here, also a smiley face. And when these solar storms get especially large, it'll spew out charged particles, such as electrons here. These black dots are my electron representations. And here's the Earth over here, obviously not to scale compared to the sun. And you can see the magnetic field lines of the Earth going from the North Pole to the South Pole. And as these charged particles come into contact with the magnetic field of the Earth, it's almost as if they get bounced off. It's like a protection, a buffer for the Earth. So they have to go the easiest way for these particles to keep moving where they want to go is to go to the South Pole or the North Pole, because that's where the magnetic field is the weakest. Go back a slide now. So here's another representation, probably marginally better picture than mine. So you can see this is where the charged particles would come. And these spirals show how the charged particles would react to the magnetic field. It's described by this equation here, R equals mv over qb, r being the radius of the curvature that the charged particle is taking, m being the mass of the particle, v being the speed, velocity of the particle, q being the charge of the particle, and b being the magnetic field strength. So here you have a particle come in perpendicular, and when it tries to get to another, if it runs into a stronger magnetic field line, for example, or these Van Allen belts, we call them, they get stuck in here and just go in this spiral, as described by this equation. And again, here's a picture of the Northern Lights They can be lots of different colors though. And that occurs because as these electrons, again, these black dots, run into molecules in the atmosphere, say oxygen or nitrogen, for example, if they collide with oxygen, what happens is some energy gets released in the form of a photon or like a particle of light. And in the case of oxygen, that gets the color that you see is red. Or if it happened with nitrogen, you'd see a blue or maybe like a purple or something like that. So for each gas, when it's colliding with a charged particle, it may release a different color of light. And this is what we might see. So that's everything. Thanks for joining me today.